So yeah, I want to talk about complexity, computational complexity. It's very fun. It's very exciting, and it'll make us better programmers. We're going to learn how fast or slow our algorithms are. We're going to have a way to quantify that. It's going to be great. Uh, let's remember everything we talked about before, like all the OOP stuff. So okay, what we got? We know now, at least, that we've got constructors, right? Constructors help us build ourselves, right? They help us initialize our own objects. Let me just give you some examples of constructors. You got what? You got a default constructor, like remember our counter class, counter, you just be like counter C semicolon, that's your default constructor. It's gonna call that with no parameters, no arguments, just like do whatever you wanted to do by default. You can have parameterized constructors, like give it 42 or something, that's a thing. Give it some value and like put the 42 into the counter's count, whatever you want. You can give arguments to a constructor like that. It's for initializing yourself. All of your member variables should have some good value in them by the time your constructor is finished. A special kind of constructor is a copy constructor. It's when you have some other object and you're like, oh, I like that one. I want it to be part of me as well in a nice deep copy way. So you can say something like this: counter make C2 out of C. Copy it into me, all of its stuff, in a way that's going to be normal and nice. Okay, that's how that works. Let's see what else. And then we got copy assignment operators. Remember those? That's for also cloning somebody, copying them into you, but you've already yourself been constructed at that point. You have some stuff in yourself. You've got your own values already. You got to get rid of them. All right, you got to get rid of them first, and then like it's already been constructed. Like let's say counter C3. C3, it's already been constructed, and you're like, you come along later, like, no, I like C3 being C2 now. So you got to, like, if there's anything on the heap, get rid of it, delete it, bring all of C2 stuff into me in a nice deep copy way. Okay, and that's the goal. And then finally, destructors. Remember that those are for you to clean up after yourself, or anything that you did explicitly. You have to, like, everything that you allocated explicitly, you have to deallocate explicitly with like a call to delete if you made stuff on the heap, stuff like that. Anything special, like those get called destructors. They get called for you one way or another when your object is about to go away. And so they're for cleaning up after yourself. All right, so don't forget about those. And yeah, I think that's all that I wanted to say about that. Time for new stuff, I think. All right. So any questions about this first? Like, remember these words? They're all still floating around in our brain. All right, so let's talk about complexity now. And again, complexity is the idea that we've got a program and we want to know how fast it is in some way, for some definition of fast, or some definition of complex. So we care about speed a lot. We care about memory a lot in this class. There are other things that you could care about, like, I don't know, energy usage, something like that, which sometimes goes hand in hand with memory and speed, but it's slightly different. So we're going to talk about space complexity and time complexity in this class. And I've told you those words before. All right. So here's my silly question for us. And it's a bi-clicker question. So if you could please open up that page and get ready. I'll start it. But what I'd like you to do is to get into groups and talk about this idea. All right. And convince your neighbors that your answer is right. But here's the setup. All right. Let's say that you are a rabbit farmer. For some reason, that's a lucrative business, and you're about to start your farm, and you can go to the rabbit Costco and buy either 2 rabbit A's, and those rabbits, like, we know that rabbits reproduce very quickly. They reproduce according to this formula, so 2000 N, so where N is days. So like on day 0, you have no rabbits, you're about to go to the store. And then on day 1, after you buy the first pair, like, they've already given you 2000. And then day 2, you have like 4,000 rabbits, right? So like they reproduce according to that formula. So that's rabbit A's, you can go buy them. Or you can spend your hard-earned startup money on 2 rabbit B's, and those reproduce according to this formula, 2N squared. So on day 0, you still have 0 rabbits, but on day 1, now you only have 2 rabbits, all right? Something like that. So my question for you is, which rabbits, rabbit A or rabbit B's, do you buy to maximize your amount of rabbits total? Does the question make sense? So please say hello to each other, talk about your break, and then answer this. I'll give you a few minutes. I'm going somewhere with this. What kind of rabbits do you want? Let's do what we want. I'm gonna go with it. What I miss? You'll have to wait and see.
So I missed nothing.
Give you another minute to discuss.
So after 2 months,
So I missed nothing.
All right, that's my timer. Let's see what we think. Let us see what we think. Give you like 5 seconds to enter in your choice. Maybe the answer is the secret option C. Let's take a look. All right. So most of us are like rabbit B. Why? Why did we say rabbit B? Yeah.
Option A is linear, the other one's quadratic.
Cool. Yeah, it's a different kind of graph if you think about it that way. Make sure we've all done attendance too, by the way. I'll stop that the next time I think about it. But I think that's a good thought. Let's see. Do I want to copy in this program or do I want to? Let's see here. So yeah, let's draw this graph. Whee. Draw both of these graphs. Honestly, maybe the answer is it depends. Like, how many days before we have to go to market?
Yeah.
Maybe that's the real answer. But if you had enough time, rabbit B's will win out, and I can try and show that to you. Like, here's the graph of rabbit A's, like day 0, day 1, day 2. On day 0, for both of them, you have 0 rabbits. On day 1, for rabbit A's, you got now 2,000 of them, right? On day 2, you've got 4,000 of them. And it's going to grow like this, right, as a line. Whee! Something like that. And yeah, day 3 is 6,000. And these 2n squared, these rabbit B's, they're not growing that fast. On day 1, what you have, 2 rabbits. On day 2, you have 2 times 2 squared, so like you have 8 rabbits. Whee! So that's a decent jump relatively, but it kind of looks like it's a parabola, right? So the question is, how many days do you have? Because eventually, no matter what number I stuck out in front of this n here, if this is a linear graph, it looks like a line, right? Y equals mx. Even if I put 1,000,000 out in front of this n, 2n squared would still win eventually. Does that make sense to us? Have we learned that? That's a thing. So I can prove that to you. So we can make a program. It's the only program I'm going to write today. Rabbits.cpp. Boop. And we've got for int I equals 0, I is less than or equal. Let's go to 1,001 days because that's going to be the tipping point. I plus plus. So we've got what? Day I. New line. We've got how many rabbit A's on each of those days. So we've got rabbit A's amount. We've got 2,000 times I. And a new line. And then for rabbit B's, we've got it's 2i squared. So you can do it like that. And then a new line to end that all off with. And so that's the program. It's like counting things. Boop. And here, so day 0, still got 0, and day 1, 2,000 versus 2, 4,000 versus 8, 6,000 versus 18. But, I mean, slowly but surely, the rabbit B's are creeping up there. So if you go down to day 999, if you wait 3 years, eventually, on day 1,000, that's when the rabbit B's will reach parity, and then they're just going to keep growing faster after that. Okay? So there will be a day, there will come a day, no matter what number I could have put here, 2,000 versus, like a million versus, I could have taken away the 2 even, eventually the n squared will beat it. All right? Eventually. So I guess if you had 3 years-ish, you want the rabbit B's. All right? So that's the secret. Any questions about that? Does that make enough sense in our minds? Just like, one is a line, one is a parabola. Parabola is going to get there eventually. Okay? And so that's kind of what we want for our programs. We'd like a graph showing, like, if I gave more information to my program, how much more complex would it be in terms of some number? So that's what we'd like to eventually create and compute. Okay? So that's our goal, measuring how complex a program is in terms of its computational complexity. So that's just the amount of resources being used by a program, time, space, money, energy. We're going to care about time and space in this class. So time complexity is how long it takes to run your program, and space complexity is how much space, how much memory is being used throughout the use of your program. So like how much RAM do you need to buy to make this thing complete? But then you might ask the question, like, there are processors and everything. My phone has a processor. This display has a processor. That phone has a processor inside of it. My microwave has a processor inside of it. I can't run the latest game on my microwave, but I know I can run computations on it still. Like the processor's slower, but I can put the same program on like this giant, like the giant computers in front of you guys, and then also my microwave. And I can have them both run, and it's the same program, but it's going to take longer on the microwave just because it's a slower processor. So there's got to be a better way, right? Instead of like counting the time, how many seconds it took to run the program, like I want consistency. So how can I time them in a consistent way, knowing that like this laptop is nowhere near as fast as your beefy desktops in front of you right now? Like there's got to be some way to like average it all out somehow. So the goal and the answer is going to be like, instead of counting the amount of time that it takes to run something, we're going to use mathematical functions. Like how long, how much like computational effort in terms of some number does this take? All right, that will be the same for any processor. So that's our goal. And the way we get there is to count stuff. All right, I'll teach you what that stuff is in a second. But here's an example of this. Like here's a loop, right? And it's adding up all the numbers from 1 to n. Okay, we see that into this sum variable. And we want to find a number that we could use to talk about this algorithm that doesn't really depend on like seconds. Just like something that's the same for any processor that could ever run this code. So one thing to be asking is like, all right, how many times will this code run its body? Because that's going to be the same for everybody, right? How many times will it run its body, regardless of if it's on a desktop or a microwave? Well, it's going to go, I is going to go from 1 to n, right? So it's going to run its body n times, yeah? And so if n was large, then it would take longer on the microwave and longer on the giant desktop. relatively, it might be shorter on the desktop still, but you get the idea, right? That can like, that's the equalizer at that point. And so this corresponds to time. That's the question. Like, all right, how, like if I count the number of times this runs its body, like is that anything useful to me? And the answer is absolutely. So here's how we can think about this. Let's count. The goal is to count now in terms of time complexity. That's where we're going. The goal is to count how many things take like one chunk of time inside of a processor. Most processors are the same in that sense. When you get to CSCI 45, you'll learn those secrets. But like, let's pretend that these are some things that processors can do in one step of time. I'm blurring some lines purposefully, but it won't really matter. So don't worry about it. So here are some ideas. Let's pretend that it takes one step of execution time inside of a processor to do all these things. So like to do some simple assignment, set one value of a variable to some other value of a variable. That takes one step of execution time inside of a processor. Another word for that is a clock cycle. If you're like engineers and you've heard those words before, that's a thing. So let's say that going somewhere into a vector, like accessing an index of a vector, that takes one step of execution time inside of a processor, one clock cycle. Let's see, what else? What else do I want to go to? Dun, dun, dun. So we say that takes like constant time. If we're going to see these words eventually, like this is going to take O of 1 time. If you've seen those symbols before or read ahead in your book, like that is constant complexity. All these things are. So you got that. Doing like math on simple things that are already variables or numbers, like x plus y, x times y. I'd say that takes one step of execution time inside of a processor. Doing comparisons, like checking to see if one thing's less than another, one thing's equal to another, all those things. So that takes one step of execution time. Let's say that it takes also one step of execution time to print the value of something to the terminal or whatever. And this one is definitely the biggest lie, but that's okay. It doesn't matter, actually. We'll learn that. So I am blurring some lines here. Some of these like take 2 steps of execution time, but as long as it's a constant number, it doesn't matter. All right. So that's the secret. Eventually we'll get there. But yeah, when I say step, I kind of mean clock cycle. That's something you'll learn about in CSCI 45 or like a computer engineering class. So in theory, like maybe you've bought a processor before, you've like read the specs of a processor. Like my processor in my laptop is 2 gigahertz. Maybe you've heard that before. That just means that it can, like, it has a little clock inside of it that ticks 2 billion times per second. And so that's what, like, it can do one step of tiny amounts of execution every 1/1000th of a second. And these are the things that I can do, let's pretend, in one step. Some of these are true, some of these are wrong. So that's kind of what I want to say there. So let's pretend that those are the things that take one step of time. And with that in mind, I want you to try counting now. So here are these things. Let's pretend that these are the things that take one step of time. Here is a program. Tell me, let's go to, I'll put this up here. You tell me, boop. Let's go to maybe, please do attendance. We'll stop that after this one. Let's maybe go to the written ice page this time. You guys can elect a leader to post your answer, but I'd like to see what you think. Honestly, the answer doesn't matter as long as you're within a constant factor of the truth. But like, try to count. Like, all right, you've got some assignments, some math, some conditionals. How many steps of time does it take to run the following code in the worst case, let's say, where you do end up running the body, like the comparison is true? All right, so you got to run every line. So please tell me, how many steps of time does it take to run this code, given that it takes one step of time to do all those things? Does the question make sense? Try to count. We'll see if we get the same number. I'll give you a couple minutes to try it and post your answer.
Additional second. Additional second. Third step. Assignment. And CF. Yes. Also additional, so actually. Yeah, should be based on additional second. Additional second. Third step. Assignment. Additional. That's cool. Let's see. Yeah.
All right, our voices are starting to die down. I'll give you another, let's say, minute or so to discuss.
Let's see.
And get your answer in there.
Yeah, because let's see. One. Oh.
Yeah. All right, let's see. Let's see if we all decided the same number. I guess you can all see each other's posts, but like, if you didn't look at that, a lot of us are thinking 9, 8, 10. Feel like that's a close to the number, right? O of 1, technically, yes, that is an answer. Good. All right, in terms of these numbers of steps, let's try to count together, all right? And let's see, I promise to stop this as well. Okay, we've got, thank you for your participation. We've got math. You need to get the answer, you need to get the 12, right, before you shove it into X. So those two things on that first line, 2 steps. It's like basic math and assignment. We've got subtraction assignment, do the comparison. Say we took the branch, the word is branch. Say we took the condition was true, we went into the body. Z equals 4, set the assignment thing, we already got 4, it's there. C out, okay, we got to do the math on Z and X to get that answer. We got to print that answer. And then we also have to print the new line. Let's say that there's 2 separate things, right? 2 separate things we're printing. So, okay, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So I got 9, but honestly, it's about 9. It's 9 steps according to our thoughts. But honestly, at the end of the day, all that we need to care about, you're going to learn very fast, is that it's a constant number of steps. That's all that really matters. So you never really have to count once I get you good at this. But that's the secret. All right. So there's that. Try this one now. All right. Or no, I guess I'm going to do this one for you. Excuse me. But with the same idea, same ideas, let's go back to this loop, and then maybe eventually I'll ask you to do something. Okay, so let's see. We've got assignment. Say we take, like, we're going to run this loop body a few times, n times, right? So like n might appear in our answer somewhere. So how does a for loop run is the next question. We've got, all right, int I equals 1. This line only happens once, right? We only run that line once. And what does it do? It assigns. So one step of time there. And then it's going to repeat all of this stuff a certain number of times, yes? And so we got to count whatever those are. We multiply by how many times that loop's going to run. So, okay, this is going to happen. Like, that's one step of time. I plus plus is secretly I equals I plus 1, right? So you got the plus and the assignment. So it's really got two things going on there, right? Like one, two, something like that. And then we got the sum plus equals I for the same reason. It's like sum equals sum plus I. So you got to do the plus and then the assignment once you hit the body. Yeah, what else? I think those are the counts for those. And now we have to, like, do the math. So, like, okay, how many things are going to happen just once? These two things, right? The initialization of the loop and the sum equals 0 part. So we got 2 out there, plus these things repeated, right? So we've got 1, 2, 3, 4, 5, right? 5 steps repeated how many times? N times, because the loop's going n times, right? So we got that. Let's see. Repeated n times, and so like this one is like it's 1, so times that n is n. Like this one is 2, so times n is 2n, 2 times n. This one is also 2, so again it's 2 times n happening. So like plus all those things, like plus I don't know, plus n plus 2n plus 2n. So is that it? There's actually going to be one more thing. Because if you think about it, like how loops run is they're going to keep running until this condition's false, right? Then they don't hit the body. They don't do anything else. So we actually need one more hit of this condition when I is n plus 1, don't we? To notice that we're done and be like, oh, false now. And we jump out of the loop. So that's going to be one more of these comparisons. So it's like, this is really n plus 1. Does that make sense? Again, you don't have to worry about this. I just want to make sure you understand it at least once. You've heard the words. So n plus 1 plus a 2n plus another 2n for the body there. Cool. And so if we like simplify, this is what? How many n's? 5 n's plus a 3. And that is apparently my analysis. Do you see how the number of steps depends on the number n? If n is bigger, you can clearly see that it's going to take more steps, right? 100 versus 1,000,000. Like, you got more work to do. When n is larger. Are there any questions about that analysis? Interesting. Okay. And then if you added a line, let's see. Say you started printing stuff, like see out the current value of sum in here. Like that would add another n, right? And just like another one thing repeated n times in the body. And that would bring out this to like 6n plus 3, just to add one more line. So honestly, we consider like this is one line away, 6n plus 3 versus 5n plus 3. They're pretty much the same. Still pretty much the same. And that will motivate where we're going next. Pretty much the same. If you added one line, it's not going to change too much. Not too much extra work to do. That doesn't really matter. The 5n versus the 6n. And we can make that very precise. All right. So our goal is to have some lingo that we can use as computer scientists to talk to people about our algorithms and how complex they are. And we don't want to be counting steps all day long. That takes a lot of time. So there's got to be a better way. The way we want to do is like simplify those numbers, those answers that we get, and get rid of any unnecessary information. So like, let's think about, all right, our analysis was 5n plus 3. So like, here's a graph of 5n plus 3 and 5n as n grows, right? You zoom out. If you zoom out enough, those graphs are pretty much right on top of each other. If you zoom out far enough, that is. All right. So like the plus 3 doesn't really do much. The plus 3 didn't really matter as n got large. All right. So n got large. The plus 3 didn't really matter. It's like, all right, 1,000,000 versus 1,000,003. That's not really doing much for us. So like that's a rule. So to simplify our analysis, let's just drop all the lower order terms because like you zoom out far enough, those are useless to us. They don't really contribute much as n gets large, and we care about when n gets large. So, okay, rule 1 can be, let's drop all the lower order terms. Like, instead of saying 5n plus 3, we'll say 5n. That's better. Faster to communicate. And then, honestly, what we really want is, we got 5n, we really want to compare our algorithms to other algorithms, right? That's the goal, like things that are really fast versus things that are really slow. And you add one line, it goes from 5n to 6n. Sure, maybe to those graphs, like to each other, like 5n and 6n, to each other, sure, they look different. If you zoom out, like it'll never change. But compare those graphs, 5n and 6n, to like n squared and zoom out. If you zoom out far enough, they all become like flat, essentially, because the parabola is growing so much faster. All right. So honestly, at the end of the day, if you're trying to compare algorithms, like to like more complicated ones, n versus n squared kind of stuff, the 5 and the 6 didn't really change anything. All right, if you think about it that way. All right, so that's another thing we're going to do. That's going to be our part of our analysis. We're going to drop any constant factors out in front of that largest term. Like the 5n and the 6n, there's just one extra line. Who cares? We'll just call that n, because really we want to compare that to like n squared, n cubed, stuff like that, and know that it's better. So that leads us to this kind of notation. So we came up with this analysis, 5n plus 3, and we want to simplify that, 5n plus 3, and we use a kind of notation called big O notation. That is their goal. That's what we came up with, right? That's what the mathematicians have found works well. So like our first simplification is, I guess we're going to count steps of execution time rather than like seconds, because it's different per processor. Then we notice that, all right, the plus 3 didn't really matter as n got huge, so we're going to ignore that. We're going to chop off that 3. Goodbye. Doesn't matter. If you think about it, like then you got the constant goes away, and finally we're also going to ignore any constant coefficients out in front of that leading term. So this 5n, the 5, goodbye. We're going to get rid of that as well, because again, compare the n, like 5n to like n squared, there's no contest. So like this is kind of what we came up with. This is our actual thing, but we're just gonna call that n because more or less it's the same. It's off by a constant. It's not really that bad. Okay, so yeah, those are your steps. So we noticed then that the running time of our algorithm, that loop, grows linearly in n, because n is like just by itself, n to the first power. So what you do is you kind of slap that number that you simplified and got out of that answer, just the n itself, you slap it inside of parentheses and you put an O at the front, and we say that the running time is big O of n, which is another way of saying that it grows linearly in n, and that's how you pronounce it, like big O of n. Okay, and so really it's the Greek omicron, but we just say big O because we're lazy. So yeah, that's how you do it. That's the analysis. All right, so the running time is big O of n. That's the simplification. Like that versus n squared, we know that the n is better. So there's that. And then anytime we have something that's a constant number of steps, like this, like 9, no matter what, we simplify that, the constant to just 1. We just say 1. It's like, because what is 9? But 9 times 1, that's the constant. We make it, we say that is O of 1 time. Okay? So that's just kind of the syntax of big O analysis. This is meant to talk about the asymptotic complexity of a function. So mathematicians came up with this. We, as computer scientists, are stealing it for our purposes. Yay. Any questions about this? All right. So normally, like I said here, like we care about how much time it's going to take in the longest amount. Like if you skip, like if this was false, you'd skip these lines, wouldn't you? And take less time. Usually we care about the worst case complexity. Like in the worst case, like, all right, how long am I going to have to wait? So that's what we care about. So yeah, because you know that some things don't take the same amount of time depending on the input, right? You can give it different values, like the numbers from 1 to 10 versus the numbers from 1 to 100. There's that. Yeah, so that's a thing. And yeah, some algorithms, like you give it just the right input so that it skips all of the branches, it skips all the if statements, skips the loop, it'll run significantly faster. And so like there's a concept of a best case and a worst case. Like in the best case, that's when everything's perfect, like the stars align. it stops raining. And that's just like the fastest your program could possibly run. Sometimes that's constant, which is kind of cool to think about. We don't really care too much about the best case usually. It's like it usually gets wrapped up into the worst case, because the worst case is like, that's how long do we have to wait really? Like how much money do I have to spend really in the worst possible case? So like think of that as like your worst enemy is picking what number to use. Every possible input is the slowest that things could possibly go, because that's what you want to optimize at the end of the day, right? If your worst case can be a little bit better, improve it, and then that might help out the best case too. So like as hopefully it is obvious, we care most about the worst case. All right, that is our goal. And yeah, because things could run differently. Like imagine you had like some big long if else, and like the if branch had like a million lines, but the else branch was tiny. Best case is the else, worst case is the if. Yeah, something like that. So with that in mind, I would now like you to try this difficult question. All right. So let's say I'd like you to figure out the best and the worst case complexities. It's okay that if you get it wrong. This is a hard question. I just want you to practice to like understand what you don't know still. All right. I would like you to determine the best and worst case running time complexities of this code over here from the if statement onwards. Let's pretend like all of this constant time, like 12 steps or something. Whatever this is, we already know that's constant time. It's a single step of execution. I want you to analyze the best and worst case of this if-else statement. Does that make sense? And I can give you those things again, like these take a single step of time. But honestly, I don't really want you to do that anymore. I want you to like put it within an O, like get rid of the constant terms and all that stuff. But you try whatever you need. Come up with numbers if you need to. But yeah, please try to write down your answer. If you're already on that written nice page, here, let me clear it out for us again. Please refresh the written nice page so we can get all back to a blank slate if you're still on it. And then you can answer it again. But here, that's my question for you. So from here on, this code right here, I'd like you to analyze it. Come up with some mathematical function. Try to do our analysis. If you remember what I just said on the previous slide, that's okay if you don't. But like come up with a number. It's going to involve some things. All right. So like, for example, you got some variables here that are used in the code. Like you've got option, could be 0 or 1. You've got n, which like controls some loops, right? We don't know what those values are. The user gave them to us. So you can't just like pretend it's 42 or something. You have to keep them as variables like we did here, if that's part of your answer. It's like, where was I? You got to keep it in, right? So that is, I think, what I want to say. Try it. Thank you. Sneeze me. So see if you can come up with some numbers. We got plenty of time to try it. Please give it a good try, and then I'll walk you through my analysis. I'll give you a 4-minute head start. Let's see. So just the if else. Got some comparisons.
Equals my nope. And that's best case. So that's
What's gonna happen? Can you see it? Now think about what's going to happen to that nested for loop. That's a little ugly, right? How does that change things? Any questions as we're trying it? All right. So press submit if you're feeling brave. I'd love to see what you thought, what you came up with. We want a best case and a worst case. Like, all right, Cloud's part. What's going to happen? What number will shine down upon us? And then when everything goes horribly, what's the other option? Cool, look at us. We're thinking linear n for the best case, n squared for the worst case. A lot of us, which is nice. Very good. We came up with some actual numbers too. I like that. I like that a lot. So let's see. Let's see what we're thinking. Thank you for trying that. And yeah, any questions I can answer before I show you the answer or show you my analysis. All right. So, again, let's pretend that option is only 0, 1, because if it was nothing, it would be constant time. If it was 2, it'd skip all of those. So let's pretend it's only 0 or 1. And let's see. Let's start with the statement. So either we're going to go down this branch or this branch. Yes. So it's either the first for loop or the second nested for loop that we're going to hit. And let's think about this. So the condition checking is constant time. There's one step of execution to do those condition checks. And with these loops, the condition check is not going to be the bottleneck. So we don't even have to really consider them because it's going to be +1 out in front of everything. So, okay, let's deal with these loops then. Okay, we've got this loop, which looks a whole lot like this one, right? Looks a whole lot like that one. So the analysis is going to be basically the same. We got sum equals 0. We're going to loop how many times? N times from 0 to n minus 1, right? So it's essentially going to run all of this stuff, which is a constant number of steps, like 9 or something. Again, I don't know. It's a constant number of steps. It's going to be run n times. That's these guys, right? C times little n, because the variable is called little n this time. Plus this thing and this condition check being true. So +2. So Cn plus some constant times n plus some other constant. Does that make sense? That's what it's going to be. I don't have to actually count now. That makes it easier on us. So at the end of the day, if we went down this branch, the check, this thing, and all this stuff repeated, is some constant times n plus some other constant. And from our rules, we're chop things off. Chop off the lower order term, chop off the constant out in front of the biggest, the highest order term, and then we're good. So this turns into O, and you put the answer between O and parentheses. So big O of n, we say. All right? This big O of n for this branch. Does that make sense? Questions about that? Please yell at me. Then this one, other option, Again, the check is going to be constant time, and then we got to deal with this. All right, we know that this loop now, because it's the same as this one, right? This loop, we know, we've done the analysis, it's going to be O of n, so it's some constant times n plus some other constant probably, and we know that that's true, and now we're running that a bunch of times, yes? How many times? Yeah, even if it was n minus 1, like the n is part of it, it's like you take the biggest thing, it's like this is going to run n times, it's going to do O of n work n times, yeah? Something like that, plus some constants out in front once you do like the distribution of all the ends and stuff. Like it's going to look something like this. You got like the inner loop is running. It's again like c some constant times n plus some other constant. And then you took all that and you multiplied it by n plus some other extra constants out in front for like the last condition and like the start of it all. Plus some other constant out here, essentially. Yeah? That's pretty much the analysis. If you think about it. Does that make sense? That's what's going to go on if you actually counted. And like you can do, like you bring the whatever it's called out in front, like this is what. You do the math. Like what is this? This is what? Cn squared plus n times k plus k2, whatever. And then doing the analysis, like, all right, the constants go away, like the lower order terms go away, like who's going to win out when n gets large? The n squared term, right? Even the n one goes away. If you think about it, as you zoom out. And then the constant out in front of this term is going to go away. So the analysis of this branch, then, is, boop, this is big O of n squared. Does that make sense? That's how I think about it, at least. And we've now got two analyses. So we could have gone down this branch over here, or we could have gone down this branch over here. And I think you can see that this one is the best case and this one is the worst case. If those are the options you get. Worst. Okay? Any questions about that example? Seems like a lot of us got it, which is great. Do we see it? All right. So, I think that is most of what I wanted to say for that slide. Now let's talk about analysis of some algorithms that we kind of already know. All right, so remember the linear search algorithm? We got like a vector or an array. We want to go look for something in it. Like here's a vector. We got some numbers in it, and let's say we've got a value that we want to look for. So it's called linear search, by the way, if we've never heard of this algorithm before. Linear is a key term. So you got a vector, you got a value you want to look for inside that vector, and like that's your job is to return the index of the value you're looking for if you find it. That's what the linear search algorithm is. So it's like you're looking for a value. You have no control at all over the vector. No control over what the vector looks like. Or it could have been an array over the vector, which means you have no clue where this 5 might be if 5 is what you're looking for. Don't know where the value might be. And so the 5 could have been at the start, or it could have been at the end, or somewhere in the middle. And so you're kind of forced to look, in the worst case, right, through everything. Go through it in a straight line linear search. So you must search through every index. And that's the algorithm. If you've never seen it, it's not too bad, right? Must search through every index. Oh man, because you don't know where it might be. So eventually I'm going to give you this algorithm in a lab. So I'm not going to implement it for you, but this algorithm and also binary search, they're all in your book. So library, what is it called? This one, SciBooks. Somewhere. We've got, I assume it's here. Yeah, so like searching and algorithms, the other one's on the next slide, but like here is linear search. There's the algorithm. So like that's more or less C++. I think you could do that analysis, but like that's the code, but I told you the idea now. Like go looking for something called a key throughout your list of numbers. They're treating it like an array where you're passing the size here, but you don't have to do that if it's a vector. Stuff like that. So that's that's that one. And we could ask for the complexity of this, right? We can ask for the complexity of this algorithm. I guess we can go back to here. It's like, worst case, you're looking for this thing called key, right? You're going through all this. Worst case, you've gone through all the values, right? You're looking for this something that's not there, and you just keep on hoping that it's there. Yeah, it's like you're looking for the number 42 through this vector. It's not there, but it could have been. So we're going through every single index, seeing if it might be there. And so kind of here's the analysis of that. Like in the worst case, you look through the whole array and it wasn't there, the vector. And so like you're going through this loop through the size of the vector times, which is, let's call that n. We like to say n in computer science. And we'll just like keep on comparing it against each element that we see there. So it's essentially like, all right, every comparison and like check and see if it's there, return if it is, find the index. Like that's like 3 steps at a time, right? That's all constant work. So at each index, you're doing a check, which is like it's 1 step at a time, doing a return potentially another step at a time, and you're doing that n times, right? You're going through every index looking for this thing that didn't happen to be there. That's the worst case. You go through everything. So I hope you can kind of see like, all right, n times constant work becomes O of n. Right? It's n times something at the end of the day with a constant out in front, which we'll get rid of. So like, that's how it works, all right? In the best case analysis of linear search would be like, oh man, it was there and it was in the very first index, right? We found it, yay. So like, what do you got to do? Like, all right, I equals 0, check and see if the thing at that index is what I'm looking for, immediately return because the condition was true. Like, there's only 3 steps a thing then. 3 steps of code, 3 lines of code, excuse me, to run essentially 3 steps at a time as well. So like 3 lines of code, if it's right there at the first index, that is constant time, all right? Constant time, which is nice. And that is not usually going to be the case, right, when you're looking for something. So like usually we care about the worst case analysis, which is going to be linear. O of n worst case time. There's also an average case, which I'm not going to talk too much about in this class, only a little bit. You'll wait until you get into like an algorithms class at a 4-year college to hit that hard. But like you can also think about like on average, it's not always going to be the worst. It's not always going to be the best, right? It's not always going to not be in there. It's going to be in there somewhere usually when you're calling this thing. You hope that it's there. So on average, like where is this thing that I'm looking for? Like it's probably about in the middle, right? On average. I think that's more or less reasonable, right? So on average, what do we got to do? We got to go through looking through half of the indices, essentially. On and about, like, go through n over 2 indices to look through, doing constant work at each of them. So it's about n over 2 steps, too. Does that make sense? So what is that in terms of, like doing some math and doing the rules? Like, this is 1/2 times n plus some other stuff, right? And you're getting rid of that 1/2. So it's still going to be, we still say linear. Still linear time, big old n time to do the average case of linear search. Any questions about that? Interesting idea, right? It's still O of n. Still the n's in there. It's cool to think about. So that's linear search. There's also binary search, which hopefully you have learned about. That's definitely something I teach, and I think we all teach here. So binary search is when you're looking through a sorted thing. You always want to use binary search if you can. So binary search, do we have an algorithm here? Binary search is a little bit more complicated, but it's worth the complication. All right, this is the algorithm for binary search. You can copy that into C++ more or less exactly. But it's keeping track of like a search space, like what part of the vector array am I looking through right now? Where it's narrowing it down, its options, like where could this thing that I'm looking for possibly be, because it's still the same as linear search. You're still going and looking for something, all right? You're still looking for some value, but you know that your array or your vector is sorted now. It's guaranteed. You cannot use binary search without it. It will not work, all right? So yeah, binary search is wonderful because you have some very strong guarantees once you know that it's also sorted, all right? And what I like to say in my CSCI 40 class is I like to pretend like this is like a guess the number game, because that's pretty much the algorithm. It's like a guess the number game that you want to play optimally. So guess the number game. If I told you guys that I'm thinking of a number between 1 and 100, what should be the number you guess first to guess it in the fastest amount of time? 50, right? You all agree? Can anybody explain why? Yeah.
Guess 50, you automatically eliminate half of all guesses.
Yeah, you want to, like, you cannot control the number I'm thinking of. And so you kind of want to hedge your bets. That's kind of you can make that precise and mathematical. Because say you didn't pick 50, right? Or wait, let's pretend say you picked 50, and I'm like, no, it is too small. 50 is too small. So now you immediately, it's not over here, right? It's between 51 and 100. You've cut off, technically 51, no, you've cut off 50 numbers, excuse me. Yeah, you cut off exactly half of it, yeah? Cut off exactly half of it. And that's the best you could do. Like you're always guaranteed to cut off 50, right? Because like even if I said it was too high, then you could cut off this one, you still have 50 numbers left. Yeah, either way, you're good. And you want to hedge your bets because you don't know which side I'm picking on. So if you made a bad guess, like, oh no, I'm going to guess 75 first, do you see how that's a bad idea? Because I could have said, like, sure, I could have said, no, that's too small, and then, like, you're golden, then you do have a smaller amount of numbers to look through, but you can't bank on that, right? What if I said, no, 75 is too high, then you cut off all that, and now you have still 75 numbers to look through. Yeah, or 74. See how that's bad? Now you have to take longer to get your answer. It's like, because you have no control over where I'm thinking, you want to look in the middle. You want to look in the middle, hedge your bets, because you're guaranteed to cut off half of your search space every time you make a guess. Like I say, that's too small. You can cut off this, and you know it's going to be between here and here now. You know to guess 50 first. You know now it's going to be between 51 and 100. Whee! And then you better believe that, all right, now the next best number to guess is probably 75, yeah? To play that same exact game now, because you don't know which side I'm thinking on, you're guaranteed for any, like, if you play this enough times with that strategy, that is the optimal strategy. You will get there the fastest for any random number I could think of, all right? So that is the optimal searching strategy for a guess the number game. It's an algorithm, right? The optimal searching strategy. And what it does is it cuts the numbers that you're looking at and considering in half each time, right? So it cuts them in half, it halves them. It halves the search space, we say. And search space is just a fancy algorithmic term to talk about what am I considering right now? What am I looking through right now? All right? It's also called a divide and conquer algorithm because it's cutting off things, it's dividing, it's conquering the other half. It's kind of cool to think about. So yeah, that same game can be played for a sorted thing. Let's say you're looking for the number 50 or something. You look in the middle, you see 38. Oh no, that's too small. You know it's nowhere over there now. Does that make sense? That's the algorithm. That's binary search. Now you look over here. Look in the middle of that. That's what binary search looks like. There's the actual code if you want to do that. But let's say in picture form, let me try to explain what binary search is going to do. So it's binary because it's cutting things in two. So, okay, let's say that we're searching for the number 4. Honestly, linear search would have done better, but it's still a good example. All right, so let's say this is your sorted vector. You're looking for the number 4. What binary search will do is it will, here's your vector. 1, 2, 3, 4, 5, 6, 7, 8. That's what I'm looking for. What do I want here? You got those. What it's going to do is it's going to guess in the middle first. Okay, the 4, maybe, I don't know, maybe 4 is the biggest thing, maybe it's the smallest thing, maybe it's the middle thing, you're going to guess in the middle first. And so how do you calculate your middle? You do it with indices. All right, the average, the index in between the end and the start, 0 plus 8 over 2, that is 4. And so that's going to be my first index to check. And so that's what binary search does. It looks in the middle first, compares it to the thing I'm looking for, the 4. So yeah, at the start, the search space is the entire thing. I haven't looked at anything yet. So at the start, the search space for your vector is the whole vector. So it's indices 0 through 8. And then you make this comparison, 38 versus 4. Oh no, 4 is much smaller. So that means if it's anywhere, it's not over here. Yeah, if it's anywhere in this vector, it's somewhere to the left of this middle. And so I can say now that, all right, the indices where it could possibly be are between 0 and 3, right? Because I looked at index 4, it wasn't there. So that's where it is now, okay? So after one comparison, you cut off over half of your search space. After, it's supposed to say after one comparison, you know now that it's between 0 and 3. Those are your indices. And so then you play the same game. This is now your smaller, it's essentially a smaller array to look through, or vector. What's the middle point of that? 0 plus 3 over 2 is 1.5, but we'll do integer division. So we'll say that 1. You got to break ties. Let's say that index 1 is the middle of it. And then you'll look there. It's like, all right, 12 versus 4. How do they compare? Oh no, 4 is smaller. So if it's anywhere, it's not over here, right? It's to the left of the thing I just looked at. So this stays the same. Could be between index 0 and index 0. Does that make sense, how we're thinking about that? That's what we just decided. It's like, that's where it could be now. And like, what's the midpoint of that? 0 plus 0 over 2, that's index 0. Let's go look there. Oh, hey, that's what I wanted. So 0 is the index where I found it. And so I took 3 comparisons total for a size 9 vector, right? Comparisons total to find this thing. And I know that linear search would have found it immediately. That's not the point. The point is that it would have taken 3 comparisons to find any of these numbers. That's the magic. It'll figure it out. It'll just go left or right depending on like how it needs to. Okay? Does that make enough sense? Like this is definitely optimal for assorted things. Like it's going to make its way around however it needs to. Like think about searching for 88. It's going to play exactly the same game but go to the right each time now. Yeah? And that's going to make it super fast. So, all right. Yeah, let's look for like what you do. Here's how it notices that it didn't find something, by the way. Like here's the code. There's a comparison here. Like you keep track of like what's the lowest index where this thing could be? What's the highest index where this thing could be? Originally it's like 0 and size minus 1. And then you keep going while you have a search space, and while you have a search space, this is what's true. Your indices have not passed each other. It's like what happens when you find something that when you notice that something's not there is your indices will pass each other, like the lower index and the upper index. So again, we have indices. Let's say we're looking for 3 because it's going to play pretty much the exact same game as for 4, but it won't find it at index 0. So 5, 6, 7, 8. So let's say the value I'm looking for this time is 3. And so originally my search space is indices 0 through 8. I'll look in the middle, which was 4, right? 38 versus 3. Play the exact same game. Oh, it's to the left, so it's here, over here, right? Oop, it's between indices 0 and 3 now. I'll look in the middle of that. What's the middle of that? It's going to do integer division, so it'll calculate index 1. And it's like, all right, 12 versus 3. Smaller. So, okay, if it's anywhere, it's between index 0 and index 0, right? Same exact thing. All right, it's between index 0 and index 0. And so it's always like when you notice your left index has never changed. It's like it could be at index 0 onwards to whatever the other one is. We're going to look at index 0 now because that's the next one to look at. 0 plus 0 over 2 is 0. You look at the 4 compared to the 3. It's like, oh no, the 3 is smaller. And the game we've been playing is when we see something that is bigger than what we expected, we change where our upper index should be. We change, okay, the biggest index where this possibly could be is the index I just looked at, minus 1. And we play this exact same game. The left index doesn't change. So it's like now, the smallest index where it could be is still 0. All the way up to, well, the game you play, like, all right, I saw something bigger. So the upper index where this thing could be is this index minus 1. It's like 0 to minus 1. That's now my search space to look through for this 4. Or sorry, for this 3. And that is obviously a place that we should not continue down towards, right? So that is not good. That is an invalid search space. Yeah? Invalid search space. And so when you don't find something, you just return -1. And so it's invalid if the upper and lower indices ever pass each other. Like this is supposed to be the lowest index where it could possibly be. This is supposed to be the largest index where it could possibly be. And now the largest index is smaller than the lowest index. So that's a thing. All right, that could happen. Even over here too, it could have been like go from index 8 to index 7. It would still be wrong. still an invalid index or invalid search space. So that's kind of what that looks like. All right, and so that's why you have this little condition right here that stops you and like, all right, it's done, return -1. Okay, so that's binary search in a nutshell. Have we all seen that before? Like, does that make enough sense? If you haven't, I mean, you can look at this code, is there, but let's analyze it because this one's more exciting, more interesting. Okay, it's faster. You can think about it. It's going to be faster than linear search. Let's discover this. All right. So okay. Worst case, running time complexity, binary search. We've got a search space. Initially, the length of it is we got 9 indices to look through this whole entire vector or array. Yeah, index 0 through index 8. Okay. So we got that, and then it's always right. You're gonna make a comparison right against your current midpoint, which is like 38. That's the midpoint of my array, the index. Then that's the value there. The second you make that comparison, your array that you're searching through is going to shrink. I mean, you don't like delete the other part because somebody still needs it, but like no matter what, you're gonna cut off either this side or this side. You're gonna go searching down the other half just through indices. That's how you keep track of where you are. And so, okay, we're trying to analyze how many comparisons at maximum do I need to make right now for any value. So like you're looking at the midpoint, you've just cut off half of your array, no matter which side you went down, then you got a smaller array to look through and play the same game with, right? Look in the middle, cut off half of it, go down one side. And I hope you can, I hope it kind of makes sense that like, all right, if we want to do the worst case analysis, we want to count, all right, how many times can I cut off the array and still have something to look at? Because the second I don't have anything to look at, I'm done, right? Does that idea make sense to us? That's going to be the worst case. How many times can I cut off this array by half and still have something to go looking through? Because I can give up the second I don't have anything left, right? So the key point is like the array I'm looking through shrinks by half, integer division half. And so the question is like, how many times can I shrink an array? How many times can I divide something by 2 and still have something left? Because eventually I'm going to have things will go away, right? So here's kind of what that looks like. A size 9 array becomes a size 4 array. Yeah, it's integer division land. But all right, a size 4 array becomes like a size potentially 2 array if you go down to the right side of it. Worst case. 4 becomes 2. You shrink that in half. You go down the wrong side. All right, now I have a size 1 array to look through. Just one index that I care about. And then if that's not there, then you know once you go down to a size 1 array to look through, you still don't find it, your search space becomes completely empty. That goes to 0. Dividing by 2 integer division actually still gets you there, right? So the number of times that I could have cut in half a size 9 array is 1, 2, 3, 4-ish. I mean, there was 5 different arrays, I guess. So if max halvings is 4, but the number of arrays, morally, it's still 5, it's still fine. Okay, so there's a number for that, right? How do I get from like 9 to 5? Do we remember the word, the mathematical function that could talk about that kind of idea of cutting things in half? Heard it? Yeah, it's going to be logarithm. Because this is like, think about it as like being exponential backwards. It's going to be the log base 2, because we're dividing by 2, right, every time. Log base 2 of n times a constant plus another constant. It's going to be big O of log base 2 of n. Because that's the amount of times you have to make a comparison, and that's pretty much the bulk of your work inside of binary search. And then you return once you find the index that you found the thing. So in the worst case, you look through the whole thing, your search space becomes empty, you've cut your array in half as many times as you could possibly do it. It's log base 2 of n times you'd cut it in half, and then also multiply that by constant work at each little mini array as it gets smaller and smaller. Do those words make sense? It's a bit of a hand-wavy idea, but like you'll read more about this. Yes?
So for binary searches, you always have to make sure your elements are in order from greatest to least.
They must be sorted. You could have it in reverse order, and like the algorithm will still work if they're in reverse order. You just have to like change the way you compare. But there needs to be an order to it. Otherwise, it'll get completely lost. Right? You'll like if there was a 5 over here, you'd like look here and then cut off this, right? So it would not at all work if it was out of order. But it could have been in the reverse order. Yeah. Good question. Yes.
If you have to sort a vector, wouldn't linear search just be faster?
Yeah, so you kind of want to, like, hopefully you were given this vector already sorted. If you weren't given it sorted, depending on the sorting algorithm that you use, there's for general things, it's n log of n for the fastest sorting algorithm for general things that you could want to sort. You can do slightly faster for integers, but yeah, if you had to sort it and then want to run binary search, then there is a trade-off to be made. Now, then it would depend on how many times am I going to look through this. Because if you're going to look through it a bunch of times, then maybe you do want to do the sorting, because then everything else is sped up. But if you're only going to look through something once, probably linear search is the better one. So yeah, there are trade-offs there, and that's a great question. Other questions? So yeah, it's like there is no right answer. I love that. It's up to you. Like it's up to your use case. So at least you can analyze it now. Yeah, any questions about any of those examples? I think I want to go a bit more precise in terms of mathematics, and that'll be the rest of it. Are you ready for it? All right. If we are happy, I want to talk about complexity theory. Like, where does big O come from? There's going to be other kinds of big O as well that we'll learn about that don't have the word O in them. Just different kinds of ways you can analyze something. But so yeah, the idea of complexity analysis, like this big O stuff, it came from mathematics, and we're talking about the growth of functions and how like asymptotically as their inputs get larger, what do they start looking like? So we stole those ideas from mathematics to use in computer science, and here are the original mathematical ideas. So all right. What's going on is, first of all, we need the idea of an upper bound and a lower bound. So an upper bound for a function, this is a weird thing to have an upper bound on, but I promise it'll make sense. An upper bound for a function is a function that is always above another function, like greater than or equal to, so it could be sitting on it, after a certain input value. So like here, our two graphs, we've got y equals x squared and y equals x. Do you see that y equals x squared after 1, 1 is an upper bound for y equals x? It'll always be above it or equal to it from 1 onwards, from input 1 onwards. Yeah. So we can say that x squared is an upper bound for x, and those are two functions. Interesting, right? So x squared, the function, is an upper bound for the other function x. It's always going to be on top of it or above it. Okay, so that's an upper bound. A lower bound is pretty much the exact same idea, just like always below or equal to something after a certain value. Could be forever. Y equals x and log base 2 of x are good examples of that, right? So like, I don't know, start it from the first value where it makes sense, like from not 0, but onwards. Do you see that log base 2 of x is a lower bound for y equals x? It's always going to be below it or equal to it. It'll actually never be equal to. That's a lower bound. Okay, so we say that log base 2 is a lower bound for x. And those are two functions, two ideas. They're always going to be below. So there's that. And that's, those ideas give us what big O really is. All right, so this is the precise mathematical definition of big O. I'm not really going to test you on this. It's going to be CSCI 26, where I really care about you understanding this. But for now, at least you can hear the words once, so they won't be too confusing later. So, okay, what we do is we're saying that some function is big O of some other function. We had our f was what? F of n, right, was 5n plus 3. And we had we're saying that f is big O of g, and g of n was just n. 5n plus 3 is big O of n. That's what we said. That was our analysis. But really, it's two functions that we're secretly talking about. And the way that we say it, like this is the definition of big O in math. It's like we say that a function f is big O of a function g if we can find two constants, the first constant c being non-zero, bigger than 0, and some other constant k, such that this is true. F of n is always bounded above by constant times g of n for every input value n that is bigger than k. All right, so let me try to explain that in picture form, but it's like g of n is an upper bound for f after being stretched by a constant factor. That's what it's saying, more or less, after a certain point in time. It's like, all right, we can pick values for this, okay? So, for example, like let me pick some, and then I'll also draw this graph. So let's see. Yeah, I think that's a good way to go. So this is fine, right? This checks out. G of n equals n. Like g is fine. Like we can say that F is big O of G, 5n plus 3 is big O of n, because I can find a constant to put out in front of G of n's output value. A good value that would make it bigger, right? I want it to be bigger than F, always, would be 6, yes? I could use 6 there, because like, if I make C being 6, right? And then also I need to pick a value to start on, but like, all right, if C is 6, then C times G of n is 6n, yes? And that's going to be bigger eventually than F, yeah? And that's all that matters for big O's definition. All right, at 0, it's going to be 3 versus 0, so it's still not bigger. At 1, it's going to be 8 plus 6, so it's still not bigger. At 2, it's going to be 13 versus 12, so it's still not bigger. But at 3, right, at input 3, then it's always going to win 6n versus 5n plus 3. So k equals 3. So from 3 on, or I guess it could be 2, because it's like greater than. So if k equals 3, then I know that C times G of n will always surpass F of n. Does that make enough sense? Like, I've picked values, like that's according to the definition now. F really is big O of G. All right, 5n plus 3 really is big O of n. And so that's kind of how that works. All right, because eventually then it is bigger. So like this is kind of what big O is saying. It's like we've got two graphs, F of n and G of n. So like, let's say that this is, I don't know, F of n is 2n plus 20, and G of n is n squared. We know, right, that 2n plus 20, if you think about it, we can say that it's big O of n squared. It's not kind of how we did it. We would say that it's big O of n, actually, with our analysis. It would be tighter, but this is still fine, right, because this all checks out. Because you could say that, all right, from, I don't know, they meet right there. So like this is like n equals 5.6 or something, where they become equal to one another. And then from then onwards, G of n is always bigger. So you can pick your constant out in front to be 1. Like, you don't have to stretch G of n by anything. It'll always be bigger just by itself than F of n after n equals 5.6. Like, just pick your k equals 6 or something. And then from then onwards, it's always going to be bigger. And that's what it means to be big O. Like, you found one function, 2n plus 20, is big O of some other function, n squared, because I found a constant, 1, that I can multiply by this G of n's value to make it always bigger or equal to F of n from a certain point onwards. That is the technical definition of big O. It's just saying that one thing is a function is an upper bound for another function after being stretched by a constant. That's all it's saying. That's our analysis. All right. So with that in mind, you can say that 2n plus 20, this example here, with our analysis, we cut off the 20 and the 2, and we say it's O of n. Sure, it's also O of n squared. It's still an upper bound, right? So big O is just saying it's an upper bound. We found something bigger. Like, that's a thing, stretched by a constant. It's also big O of n for the same reason, right? Because you can find 3. Like, choose 3 to be your constant. That would beat out 2n plus 20 after a certain amount of time. And it's also like 2n plus 20 is also big O of n cubed, isn't it? It's like, all right, eventually n cubed would win. It's bigger. Like, that's what it means. It's just like it's a greater than sign if you read it backwards. That's more or less a thing. Yeah, so it's like, some people write it like this, F equals big O of G, but like, it's not an equality. It's a little weird. It's like a club. Like, it's within this club. Here are all the members of the club. F is all of these things. Okay. You can read that if you want, if you know those terms, know those symbols. But yeah, F is big O of G just means that, according to this, right, F grows no faster than G after being stretched by a constant. Okay, and so G is an upper bound to F. That's all it really is saying. G is an upper bound to F. That's what it means to be big O. You are an upper bound. So all of these functions are upper bounds to 2n plus 20 after being appropriately stretched by a constant and waiting an amount of time for them to be winning out. But usually you want the best one, right? You want we call it the tightest bound. You want the one that's going to give you the most information, and that's for sure O of n, right? That, like, you've lost information once you say, oh yeah, that's n squared. Oh yeah, that's O of n cubed, right? You want to be as small as you can be. That's the best analysis, all right? That's what we care about. But yeah, at the end of the day, it's just big O. It's always an upper bound. But we care about the best upper bound, okay? That's what we want to think about. And I think that is most of what I wanted to say. Does that make any sense at all? I'm not going to test you on this, but this is where the big O definition came from. Like, this is what mathematicians are using it for. It's like one function is bounded above by another function after squishing it or stretching it appropriately. So yeah, that's how that works. We want the best upper bound though, all right? And so here, you got like a fun little website with some algorithms that you might know about already. You got the big O cheat sheet. Here are different graphs like big O, constant, logarithm, big O of n times log of n squared. You got exponential 2 to the n factorial is even worse than that. You want to make sure your algorithms are within the green zone if you can, right? Like here's a bunch of things like for an array, to access an array, it is O of 1. Do not worry that it's a theta right now. Think of it as O of 1, constant time. To search through an array, worst case, or average case and worst case. Linear time, cool. And then they start using O's for worst case analysis anyway. It's like upper bound, cool. We'll learn about these data structures, like linked lists. Interesting. We'll learn about this one. Cool. It does some things. It beats out arrays in a certain way. Stuff like that. Constant versus linear. Blah blah blah. So yeah, that's just a fun little graph. I just wanted to show you the graph. Like this is how they all compare to one another, and that's why we don't really care about the constant out in front of the n log n or whatever. Just like how does it compare to like n squared to n? Like you always want it to be better. Closer to the axis if you can. Yeah, that's what complexity looks like. And we've got terms for this, by the way. So O of 1, that we call that constant time. I told you that. O of n was linear time. We said that already, right? O of log of n we call logarithmic time. Makes sense, right? N log n. People usually just say n log n, but apparently the fancy term is linearithmic time. Sure, linear plus logarithmic together. N squared, n cubed, all those things are polynomial time, we say. And then even worse than that, you get some really disgusting looking algorithms. We got exponential time for those, where the variable is the exponent. Disgusting. So yeah, at the end of the day, I want you to just use our rules that we learned. That's going to give you the right tightest bound big O analysis, like count the steps. Like, oh, this takes 3n squared steps plus 72n plus 42. The analysis of this is going to be, it's always like chop off the lower order terms, even the one with the n, because the n squared is going to win. And then chop off any constants out in front of that leading term. And so then it's like, our analysis is big O of n squared. Because you know it could also have been now big O of n cubed, big O of n to the 4th, big O of 2 to the n, but that you've lost information at that point. You want to give the tightest bound, we say, right? And that will give it to you. That is, I think, everything I wanted to say about complexity for the day. Are there any questions about anything we talked about? So not a lot of code, just a lot of ideas. So we'll come back to this next time, but I think that's where I want to stop today, not put any more things into your brain. So yeah, it's the start of computational complexity, exciting. And there's plenty more to go, plenty more places to go from there, but that's enough for today. We'll finish these slides next time. We'll talk about your lab next time, and we'll also talk about your midterm next time.